Alright, good day. Now let us start with our subtopic here called separately excited DC generator. Now at home, remember just now in my introduction I mentioned about elevators, I mentioned about electric drill, electric car, these are all motors. But now we are going to talk about the first application of DC machine, which is a generator. Alright, before I move on to generator, let's go back to our revision. Now a generator needs magnetic flux with motion to generate electricity. Alright, as this diagram says, I have a pair of permanent magnet here, then I have the presence of magnetic flux, and if I have this conductor and I move my conductor up and down, alright, moving conductors react with the magnetic flux, produce electricity, and if I have a bulb would then lights up. Right, so that is a very basic generator action. Now if I were to put it into an equivalent circuit diagram here, I would have this. So this diagram here is called separately excited DC generator. Now why do I call it separately excited? Because there are two circuits. Now the inner circuit here is the magnetic circuit. Right? This is the field voltage, field current, field winding resistance. Remember what I said about electromagnet previously? If a current passes through a solenoid, it becomes a magnet. Alright? So this is an electromagnet. So the inner circuit here is your magnetic circuit. The higher the voltage here, the higher the current, the stronger is the magnet. Alright? And over here, the outer circuit is called the armature circuit. Okay? And this structure is called the armature. Now what is inside this armature is conductors. Remember we say about this conductor here? So here is only one piece of conductor that I draw. But actually in this armature, it could be like 1,000 pieces of conductor or 2,000 pieces of conductor. So there are many conductors inside. And they are being wound in such a way that they form circuits. So this structure, we call it the armature. And this arrow here represents the cranking motion. I'm moving the conductors. Right? So these moving conductors react with the magnetic field, will produce voltage. And this is therefore the symbol for generated voltage. And RA is the armature winding resistance. It represents the resistance of the conductors inside. Remember I said 1,000 pieces? How many ohms they are, I pull out and show it to you outside here. Okay? And the current that flows in this complete circuit is called the armature current. And this represents the output. For example, the lamp here just now that I had. Right? The lamp. Alright, so this is called the load. Okay? The resistance of the load, and the voltage across the load, we call it the load voltage or the terminal voltage. Alright? Now, just before we get even more detail, let's go through the English word. Right? EG is generated voltage. This structure is called armature. RA is armature winding resistance. And IA is armature current. VF is field voltage. IF is field current. And RF is field winding resistance. Right? Can you identify them in the circuit? Let's go through it again. This circuit is representing the magnetic circuit. Field voltage, field current, field winding resistance. The higher the VF, the higher the IF, therefore the stronger is the magnet. This is armature. What is inside the armature? It's a group of conductors. Could be 1,000 pieces, 2,000 pieces, 3,000 pieces. This represents the motion. A moving conductor. I move the conductor in the presence of magnetic flux, produce a voltage, and this is called the generated voltage. And this is the resistance value of the conductors inside. We call them the armature winding resistance. And this is the armature current. Okay? Alright, with that, we are now going to go through some simple calculation based on this equivalent circuit. Okay. Right, if I want to calculate IF using Ohm's law, V over R, it will be VF divided by RF. Right? And if I were to write a Kirchhoff's voltage law equation for the armature circuit, it will be EG equal to IA RA Ohm's law, I times R plus IA times RL. Right? So that's my KVL equation. So from this equation, if I know EG, I know RA, I know RL, can I find IA? Of course I can. It's a simple mathematics, isn't it? Then I want the power generated. Power generated is if I use I times V, then it will be IA times EG, because the voltage generated is EG and the current that flowing out is IA, so I times V. Yeah. If I want the output power is the power in the RL. Okay. And if I were to use I times V, it will be IA multiply VL. Okay. Or if I want it to be I square R, then it has to be IA square RL. So that is the output power. Okay. Now, what if I want you to calculate the power loss in the armature winding resistance? The power that dissipated in the armature winding resistance is the loss, because it's not doing useful work, dissipated in heat. So power loss in RA, I use I square R, it will be IA square RA. Got it? So these are the basic calculation of separately excited DC generator. Okay, now before I end this topic, can I give a quick questions to you here over this generator action? How do I improve the voltage generated? Do you think it will be improved if I make my magnet a stronger magnet? Yes, right? Or I move the conductor in a faster speed. Do you think it will generate a higher voltage? The answer is also yes, right? Or I put in more conductors, put them in series, and therefore I have more conductors, so more voltage is being induced. So in order to increase the voltage generated, I can increase the magnetic flux, I can speed up the motion, or I can put in more conductors. Alright, and that sums up our separately excited DC generator. Thank you.